Okay, welcome back. Welcome to the afternoon keynotes. We are going to keep the fun going. We're going to not just keep the fun going, we're going to expand your mind a little bit with the next couple of keynotes that we have this afternoon. I do need to, though, kick things off by sharing with you one of these forward-looking statements. And for those of you who were with us Monday afternoon, you might remember how much fun it is for me to present this slide. So just take that in. And this is especially for Mark Papermaster, AMD's Senior Vice President and Chief Technology Officer, who will be presenting second in order and will close down the keynotes for us today with his vision on surround computing. But of course, we'll be making some statements that deal with forward-looking matters, future technologies, intentions, and plans of AMD. I do have one other significant thing to make you guys aware of as we are here in the second half of our third and final day. We really want your feedback on the AMD Developer Summit, or APU 13 as it's called this year. You guys may have seen outside of registration those kiosks where you can take the survey. You can also download the APU 13 app on Google Play and the Apple App Store where you can take that survey. If you complete it for all the different technical sessions that you went to, and you complete 7 or more surveys by 6 p.m. today, you'll be entered for a chance to win a 1-year Adobe Creative Cloud membership. So all those technical sessions that you've been to, all those things that you've done, big incentive for you to go. Fill out those surveys. Let us hear from it. Let those who invested all that time in those technical sessions hear from you. And then you've got that great chance to win the Adobe Creative Cloud membership. Okay. With that, mind you, why don't we talk a little bit about what's next?
Yeah, I think we're continuing the trend from the morning's keynotes. We're going to present to you yet another very important and compelling keynote on gaming. And this time we have Johan Andersson. Johan Andersson is arguably one of the top 3 game developers in the world. He's responsible for the Frostbite game engine. Frostbite game engine was an engine developed by DICE, the Swedish game company, and subsequently acquired by EA. So now he technically works for EA, but mainly on the DICE front. He is responsible for the entire Battlefield series. In fact, on the other side of the convention center, there is a fan day going on with Battlefield 4. And there are about 1,500 very loud and rousing game enthusiasts out there. We kept it on the other side so that it wouldn't disturb our conference. But I think you should go and look at that because it's a lot of energy. And Battlefield 4 is probably the biggest game of this year, maybe of the last few years. Now, the thing about Johan is, despite all the effort he has to put into coding game engines, and game engines are amongst the most complex code ever written, he's also on social networks 24/7. But I asked him how he started in this, expecting, a slightly unusual answer, and I got a really unusual answer. It turns out he went straight from high school. He lugged a PC to DICE headquarters. He had written a game engine himself. He went and showed them the game engine, and they were so impressed, they hired him straight into DICE, and that was the original genesis of the Frostbite game engine. So there's hope for the very gifted. So with that, let me introduce and let me call on Johan Andersson to come and tell you about what he's doing.
Thanks. It's good to be here. So I'm here today to talk about Mantle. And Mantle is a really exciting project I've been working together with AMD on for quite some time now. Mantle is really a low-level graphics API with the main goal of improving performance and making it easier to develop advanced game engines in general. So we've been working with adding support in our engine, Frostbite, and specifically for Battlefield 4. And this is this has been going. Oh, damn it! My slides are auto-advancing. They should not be auto-advancing. Please disable that. Please go back and disable auto-advance. Okay. Let's restart a little bit. The main goal of Mantle is to improve performance and to simplify advanced game development. And we really want to try and give developers a lot of a lot of freedom to be able to build innovative graphic solutions. And I think also Mantle is a little bit of a method for us to sort of challenge the way things are done and challenge the status quo and make interesting games. So going forward, this talk is really about how Mantle works for developers. We have some learnings that I'm going to share of the work we've been doing with Frostbite, but also in general, just going through the various areas of Mantle and how it can impact developers. So you can sort of see that in 5 different areas of how we can give more control, how we can improve performance and programmability, and sort of a little bit about various platforms. So starting on when it comes to control, we have the model that we have in my slides are still auto-advancing. Please disable that. Okay, I think they're disabled now. Okay, perfect. So with Mantle, we have a model that we like to call a lot more explicit model than the sort of traditional model of DirectX and OpenGL. We're working on a much thinner, lower-level abstraction that exposes how hardware really works. Compared to DX and GL, that's a little bit, we could say, the middle ground abstraction. It's a compromise between performance and usability. And unfortunately for us, everyone sort of have to work on that. With Mantle, we moved to a lower level, and one way that sort of shows up very clearly is that we've moved to be able to work with memory a lot more explicitly. Memory is a responsibility of the application compared to in DX and GL, the traditional models where memory is hidden away behind resource objects, and state for resources is hidden as well. This also enables our resources to become globally accessible instead of having to go through a device context like you do in DX, where all resource updates go through a specific objects in order to be pipelined and update this sort of hidden memory and hidden resource states. And this leads to some pretty interesting behavior. If my slides can advance, yes, where we can manually describe the behavior. Okay, I guess they're changing my slides now. Great. Okay. So we go back to a model where what the state of resources is explicitly defined by applications, and we also have to transition them manually between, for example, if you use a texture as a render target initially, and then you want to use it as a texture, that's an operation that your application have to explicitly define, compared to how it works in DX, where the driver is actually quite a complex driver that analyzes every single draw call and goes through them and see if you're setting a texture, was this used as a render target before? It has to sort of implicitly do various operations for them. So this brings on quite a few different interesting new responsibilities onto applications. And you have to describe the case of render targets and how you have to sort of transition them manually from between the various states. There's a lot of other types of transitions that applications have to do. But there's also things like with explicit memory management, you can't just delete the resource that's being used by a GPU while it's running. It will essentially crash. The application is responsible to make sure the lifetime of resources is tracked properly, either through fences or tracking them over frames. And functionality like dynamic resources that exist in DX and GL, where the driver automatically does resource renaming under the hood, becomes the application's responsibility instead. Similar also with memory tiling, where you tile resources for performance. So this is quite a lot of responsibilities to take on, and it's not really for everyone, for all applications. But we do get quite a lot out of this. And there's also a validation layer in Mantle that's a really powerful component to help with these things, to make it easier to take on all of this responsibility. So what does all this give us? There's quite a few things that we, as an application and a game engine, we have the information about our full scenes, so we know what we're rendering, we know what we're simulating, we know where all of the objects are in our scenes, and we can adapt these use cases in order to do various types of performance and memory optimizations for this based on this full scene information, this high-level information that the drivers in traditional models do not have. And one concrete example for that is that on the consoles, we often use linear frame allocators because we have explicit memory access on consoles and usually unified memory. So linear frame allocators are pretty trivial to implement in Mantle as well, where instead of tracking every single object, you essentially just use larger memory heaps and linearly increment on them. We also know how we stream in data within our game engines, how we load various sections of our levels, and it's fairly trivial to connect that together with specific memory pools and just load and treat memory as a big whole as we're loading. We know how our games are loading that data. We can also use pin memory, for example, if we know that both the CPU and GPU will cooperate on the same memory location. And overall, an important thing with this explicit control is that it enables us, as sort of large advanced game engines and applications, it actually reduces the development time for us overall. The initial time to get something up and running is a little bit longer than with the traditional model, but the overall time of getting to sort of what good looks like when it comes to performance and robustness is reduced. Because we can take on more work initially and utilize that across multiple titles. So there are a couple of other things that gets enabled by this explicit control. One is transient resources. In the traditional model, render targets are a pretty big, complex resource that you have to sort of create upfront, and that takes a lot of memory, especially in the modern type of rendering pipelines that we have today. With this explicit memory management, we can alias these render targets and save a lot of memory. We don't have to pre-allocate everything. It's actually easier to use. And with a lot of responsibility being moved from the driver over to the application, the hope is also that the actual driver will become significantly easier to develop and maintain, and, of course, reduce CPU overhead. So that brings me into CPU performance and how that sort of impacts with Mantle. And we have a couple of different components here that are important, or a couple of different concepts. There are three key concepts I would say in Mantle. One is descriptor sets, and one is monolithic pipelines, and also command buffers, and I'll go through them here briefly. So descriptor sets is really a way of how you tell which resources to use on the GPU. Resources in a traditional model are bound by usually a one-to-one basis, or we're binding textures to individual shader stage. This replaces that with a large resource table of quite simple resources. Either you have images, that could be textures or UAVs or anything image-like, or you have simply memory, which is essentially buffers or just raw views of things, as well as samplers, and then you can also link between resources. And this is a quite interesting model. It's a little bit difficult to wrap your head around it, but I have a couple of examples here of how it can work. And all of these resources are, descriptor sets are managed by the application. So there's a lot of opportunity to optimize for a specific type of cases that you have in your game engine. So here's one very simple example. This is actually probably not the most ideal way of doing it, but this works. It simulates a little bit how it works in DX and GL. So here we have a single dynamic descriptor set. So with a bunch of resources, we have vertex buffers, we have vertex constants used by the vertex shader, and we have 3 textures and a sampler as well. So these are the resources that will be accessible for the following draw calls, essentially. This is very similar to how it works in DX and GL, except that you see one of the textures, texture 0, is being used by both the vertex shader and pixel shader, but it's represented just by a single slot. So this is a simple way of get things up and running. But a more interesting case is this, where many of our objects are actually static, or not necessarily the data of them, but the list of references that we have for them. When we load in the mesh, we know that it's going to use it's definitely going to use a vertex buffer, it's going to use a couple of textures. Usually we know all of this up front, and the samplers, which is the texture filtering modes and stuff like that, are the same. They're usually really quite static. So we can actually just allocate a static descriptor set up front and just link to that one. So for every draw call, we have some dynamic vertex contents in this case, and we just link to the static descriptor set. So we don't have to go through and set all of these resources for every single draw call. It significantly reduces overhead here. And this model is actually closer to how hardware actually works, and so it's efficient on that level as well. Another of the concepts I mentioned are pipelines. So In Mantle, all the different shader stages are merged together to a single object, together with important pipeline stages, such as what type of render target right mask you have, or alpha blending modes, or some select graphic state. So all this is put together into a single object. And the reason for that is that we can completely avoid runtime compilation within the driver or patching of these shaders. And it's up to the application to create these objects. You could create them dynamically if you want. It would be similar to how drivers work today. And perhaps you have a very dynamic use case, so you have to. But ideally, you should create these a little bit more, statically, and you can even cache them on disk. And that can significantly improve performance also just with switching between lots and lots of shaders. There can be some impacts on memory when it comes to these things, but modern machines have quite a lot of memory, so it's usually not too bad. And the last thing, it's pretty simple. It's just command buffers. All the existing drivers work with this already. This is just a layer on it that actually exposes it to the application in an efficient manner. So you bind the graphic state, the descriptor sets I mentioned, the pipelines you want, you do your draw calls, you set some high-level state like render targets, and all these are completely independent objects that are really efficient to create, and you can have multiple ones per frame. You can even reuse them if you want to. And this is in contrast to how it works in the traditional models. So in DX and GL, you have something that looks sort of like this. So here's essentially 3 frames. The game is being being updated on CPU 0. When the game is sort of getting more, game frame is being done, we do a rendering thread that issues our DCD or OpenGL commands. And then the driver takes all of those commands and it essentially just records them and plays it back on its own thread. And this model is quite good in the average case, actually, because it automatically gives you a lot of, it sort of extracts out a lot of parallelism automatically for you. So it scales quite nicely for a large set of apps, but it scales very badly to many CPU cores, and it's quite limited in that way, and it also adds additional latency, and this specific driver thread can collide and become a bottleneck. We see that quite often in Frostbite. So with Mantle, we can do this instead, which looks a lot more nicer. Where we have the game thread running its 3 frames here, and then at the end of the frame, we just go wide and update our rendering. And this has a lot of benefits. We can scale much more nicely. We don't have any driver sets that can collide. It's lower latency. And this is actually the exact model that we're using on all of the consoles, both the last generation consoles and the current generation consoles. And with Mantle, we can do this on PC as well, which we do. With great performance improvements, which leads me into GPU performance. So thanks to all of the sort of CPU performance improvements that I've been talking about, CPU with Mantle should never really be a bottleneck for the GPU anymore. So you could actually use the CPU to help the GPU a little bit more, do a little bit less brute force rendering. Sometimes we have to brute force it through because we're so limited by draw calls, or it can improve calling, or just spend the extra CPU time on the overall game. Either is fine, of course. But there are also other optimizations that can be done with Mantle. The monolithic shader pipelines that I mentioned gives the driver quite a lot of opportunity to optimize its usage. It can actually optimize based on this overall knowledge of how all of the stages are connected and see if there's some cross optimizations that can be done from that. So it's nice to be able to give the driver in critical areas some extra opportunity here. We also, with the resource states, is in a similar fashion there. Where the driver gets full explicit information on when we need to switch between various states, and us as an application can also see if we're actually switching a lot that could actually result in lower performance. So this becomes explicit and easier to track. And finally, there are a bunch of sort of existing GPU functionality that's not really exposed in DX that we can use. Simple things like just extra primitives, quads, and rect list for efficient 2D rendering. And a little bit more complex things like MSAA, where you can use specific hardware acceleration structures and expose those to us as a developer. And all modern GPUs are really quite complex, heterogeneous machines that have multiple individual engines. So you have the graphics pipeline as one engine, you have one or multiple compute pipelines, and you may have DMA transfer to just transfer memories, or like video encode or image encode and decode. And Mantle exposes these as queues for these individual engines together with synchronization primitives. And this can, so here's an example of just in Mantle, for example, just we recorded a command buffer with graphics commands, and we're submitting it to the graphics queue that we have together with some metadata that it needs to be able to execute. So we just add work into these individual queues, and the system and GPU will just pick up this work, and you can all do all of these independently. And there are a lot of cool use cases that gets enabled by these queues. So a very simple case here is asynchronous DMAs. Here we instead of blocking the GPU execution and blocking all ALU work in order to copy a resource between a few stage, perhaps this is a render target we want to use in a later post-process effect, we can issue a synchronous copy with our DMA engine and do some other useful graphics work in the meantime. So that's a very simple use case that gives good performance improvement. Another one is to be able to do asynchronous compute together with graphics. And the key idea here is that you'll have some graphic stages where you probably are bound not really by ALU, but by the overall ROP or be bound by memory. For example, shadow map rendering is usually not that ALU heavy. So in this case, we've moved lighting to be able to run in parallel with our shadow map rendering, and there's a bunch of small async compute work there of processing just a very ALU-heavy lighting that can be run at the same time and fill up the machine better and get out some extra performance from that. Yeah. Another interesting use case, we haven't really done this yet, this is more R&D or just thinking about it, is to be able to run multiple compute kernels in parallel and have them collaborate with each other. Instead of creating a large compute kernel, sort of like a Uber kernel that can do a little bit of everything within it, you can create, in this case, like a producer-consumer type of pattern where one compute kernel is generating work for another one, for example, doing your own custom rasterization, conservative rasterization, or anything really. And this can go on at the same time as graphics work is issued as well. And finally, one use case that we've been a little bit inspired about from PS3 is essentially we have the graphics pipeline issuing individual draw calls and processing them and rendering them. And these are essentially atomic units that we send to the graphics pipeline, and we could use compute to simplify the amount of geometry that we're sending down. Instead of having the CPU issue more draw calls, you can have the GPU call its geometry or process it in different ways. Having a big destructible building actually is quite a lot of redundant geometry that we're rendering for each view that takes extra graphics time. So you can have the GPU helping the GPU, which is quite interesting. And I think you'll see going forward that game engines will sort of move to a little bit more to this model overall, where you build large GPU job graphs and move away from single sequential submission, just as we've done on the CPU quite a while ago. And which these queues also sort of bring me into more general work general area of programmability when it comes to Mantle. It's a pretty important aspect, and a very simple area is actually multi-GPU. It's supposed to be a simple area, but traditionally there's really not that great APIs to work with here. But with these queues that I described fit very well into the multi-GPU territory, where you can have multiple GPUs in the same system, and all of them just expose their own queues. So you'll, in this case of 4 GPUs, you'll have 4 different graphics pipelines, all that can run independently. In this case, with different memory, which can be a little bit tricky, but you can implement your own alternate frame rendering here to get good utilization of all of these. Or you could do something a little bit more exotic. Like, for example, one use case we're interested in is to be able to see if we could build workstations with 4 or even 8 GPUs for really super high-end rendering and simulation, not necessarily for just consumers, although there probably are some high-end consumers that want this also, but mostly for ourselves to play around with, to see what we can do with 40 teraflops in the same machine. So in this case, you could have build these large job graphs that are described on the GPU with these different queues and have them execute on individual GPUs. And alternate frame rendering typically breaks down if you use this many, so you'll probably split up the work a little bit differently. And another way of using queues that's a very different use case is just for low latency rendering, which is very important for VR or for competitive games, where you can have a sort of a latency optimized way of executing these job graphs and try just to finish off work as quickly as possible. You sort of have to balance memory transfer versus compute in this case. A VR case is also very simple if you have just 2 GPUs. You just dedicate 1 per GPU and issue work to them completely simultaneously instead of having individual frames going to each one. There are also a couple of new mechanisms that gets enabled by Mantle that GPUs also have. And one is command buffer predication and flow control. It's sort of a more advanced way than draw indirect or dispatch indirect, where the GPU can affect or skip work that's been submitted to it. We have a bunch of ideas of how we can use this for more sort of advanced variable workloads and advanced culling optimizations. For example, you can, thanks to another mechanism, where you can write occlusion query results directly into a GPU buffer and use that on the GPU without having to go through the CPU. You can implement your own predicated rendering by, well, you render a Z buffer, you issue some occlusion tests for that, and directly based on that results, you decide on how the GPU frame will be rendered. Or you can just use it for solving like age-old problems of lens flares and visibility of them, where here the GPU will actually know in the same frame if the specific lens flare is visible or not, instead of having to go through a multi-frame round trip over the CPU. And a key mechanism or for programmability with Mantle is bindless resources. This is sort of just an extension of the descriptor set support, and it's a really quite important key programmability, well, programming primitive, I think, going forward, because it allows shaders to select resources and decide which resources to use directly themselves, instead of having this sort of static binding that's set up front from the CPU. So you could use this for just general optimizations, for example, just sending less data down from the CPU. Or you can use it for building more complex data structures. And there's some algorithms that are very difficult to build with the current structures. For example, if you do a ray tracer or even some deferred texturing scenarios where you want to have a material representation. So for ray tracing, perhaps you trace through your ray and you'll hit multiple different types of triangles, and all of them can have different materials. You need to be able to, from a data structure in your shader, be able to look up exactly what material you're using. And this is possible to get with Bindless. So that's really quite exciting. And that was it for the programmability aspect. There's also quite a few components when it comes to actual platforms that Mantle can run on. So today, Mantle is for Windows. We get really good improvements both for Windows 7 and for Windows 8 when it comes to performance and with all of these controls. And it's a little bit of an investment in initial development time for it, but for us at least, it's really well worth it. Though one have to say that DX and GL is really the industry standards today, and we do absolutely need them for platforms that do not support Mantle. And there's also a strong use case to continue to use them for developers that sort of don't need or not really want this type of extra controller performance. Perhaps you're targeting a completely different type of topics there. So we do have to build and continue to maintain our OpenGL and DX rendering path, but we really try and avoid limiting ourselves to what we can do in those APIs. So I think going forward, the main things that will sort of drive the designs that we have in Frostbite and the type of optimizations we do will be what we can do with Mantle, and also what we can do with PS4. PS4 has also its own graphics API that's really quite programmable and really quite a lot of good control and performance from it. So we can share concepts and methods and various types of high-level optimizations between those and see where we end up with that. This is quite exciting. And there are also a couple of other platforms that I think is of interest. Both Linux and Mac would be a really good fit, in my view, for Mantle. It would enable us to bring up our full engine and our full render a lot quicker than it would be with OpenGL, and I think the end result would be quite superior in that regard also. That said, we are building an OpenGL renderer today within Frostbite. But there are a bunch of use cases for this. For example, the workstations that I mentioned, it would be quite nice to actually run those on Linux, where you have more control over these quite specific things. There are also R&D one could do on these platforms and not be limited by what you can do with VDDM. And finally, games, especially with SteamOS coming out there next year. That together with Mantle would be a really, really powerful combination that would be interesting to try out. There's also a couple of other types of platforms. The mobile architectures that exist today are really getting quite closer to desktop GPUs in capabilities, not necessarily in performance just yet. And in mobile, you're even more constrained by both power, bandwidth, and overall performance. So having a lower level API that can really utilize the hardware and allow applications to play more nicely with it would be a very interesting topic there. And I think it's a major opportunity with Mantle to, if you would have mobile SoC vendors or platform providers using it, it could really leapfrog what you can do both on GL and on DX. And finally, the pink elephant in the room when it comes to Mantle is multi-vendor support. And Mantle is really designed to be a thin hardware abstraction. It's not tied to the AMD's GCN architecture. It's been designed with that in mind, the actual architecture and what we can do with it and actually expose that, but it is a hardware abstraction, and one that is forward compatible and one that has extensions for things that are really really architecture or platform-specific functionality. A little bit similar to GL here, but a lot lower level type of extensions. And I would say that, I believe that Mantle would actually be a much more efficient graphics API for the other vendors as well. And it would be really interesting to investigate that in more detail once we're sort of done proving out that Mantle works with our games. And most of the functionality that I talked about today can actually be supported on most of the modern GPUs. So I would like to see a future version of Mantle that is supported on all platforms and on all modern GPUs. This is a pretty tall order, but we're going to try and make a push for it at least and see where we get. Ideally, it should become an active industry standard with multiple IHVs and ISVs sort of collaborating on it and really enable us developers to easily write games and complex game engines with great performance and programmability sort of on all platforms, including mobile, ideally, in the future. And finally, I have a bit of a section of some of the work that we've been doing with Frostbite specifically. So first of all, we have a video. In case you haven't seen the work we've been doing with Battlefield 4. If you can play the video. So that was some Battlefield 4 footage from our multiplayer. That was not running Mantle. That was just in general to describe what the game is. We're working on a Mantle renderer for Battlefield 4 and for Frostbite in general. So we've been working quite a bit on bringing up our core renderer. It's actually quite interesting that it's looking a lot. The actual code looks a lot closer the code looks a lot closer to how the rendering API on PS4 works than it looks at on DX11, thanks to the explicit memory control and sort of the quite low-level primitives that we were working with. And we have quite a lot of different rendering effects and techniques that we're implementing for BF4 right now they're already in the game, but they only works for the existing paths, so we're bringing it up on Mantle. We've been working quite a bit on various CPU optimizations, like the parallel dispatch that I've talked about, and the Descriptor set that should give some really good performance improvements, and also doing some GPU optimizations specifically with MSA and just minimizing transitions. And ideally, we'd like to do a bunch of more R&D and seeing whatever more GPU optimizations we can do. As we have to manage all memory ourselves, that's also a pretty big part of the work. And same with multi-GPU, we have to implement fully ourselves. We already have pretty good multi-GPU scaling, but this should run even better because usually with multi-GPU you get CPU bound in many cases actually. And it hasn't been that much work actually. It's been spent around 2 months we'll be spending around 2 months of work on bringing this up. And we're targeting an update in late December. And after this, we actually have another game that we're going to bring over. So we have a video of that one also.
Hey, come on, let's damn thing. Come on,
Thanks. We're really happy about that game. It's pretty awesome. It plays very well and looks really, really nice. It's a very different rendering from BF4. But I think Mantle will actually be a really good fit from that. We'll bring over the work that we've been doing on BF4 and the work we've been doing on, on Frostbite in general with all this, and it should just work out of the box running on Mantle this. And we'll focus a little bit more work on sort of APU performance on this, because it's a little bit more, I shouldn't say casual title, because it's still 24-player multiplayer, but it's a little bit more, even more accessible title. So we want it to run really, really, really well on laptops. Actually, BF4 runs quite well even now on the new Cavalry, but this will run even better. So that would be quite fun to work at. And then going forward in the future, the goal for us is actually the work we've been doing before and then later with Plants vs. Zombies is just going straight into the main Frostbite version that we have. So all of our Frostbite games going forward will be designed with Mantle. And we have around 15 games in development across all of EA. And this is an example of some of the studios and games that we have, the ones that I can share today. And going forward, we'll also like to do some even more advanced sort of R&D and experimentation with Mantle and what type of rendering use cases we have. The games I've talked about, those are games we're porting over. What happens when you actually design a game from start with it, based with the engine and based on what we can do on consoles and with Mantle? That would be extremely, extremely interesting to see. And we also would like, just to reiterate, would really like to be able to have a future where we can have this on all platforms and on all vendors. So that's all for me. Thank you.